compound spelling count. So it's Ag2SO4. Let me do it. Let me work it out first and see if I have it right.
Okay, that's what you have, right?
Where is my conference call? Okay, oh, right here. Okay. Yeah, I'm gonna open it on my laptop.
Okay. Hi, Tara. We're getting a couple more people adding on, which is good because a lot of people are having trouble getting on because of the power problems they've had with Canvas on school. So we got about 3 people, maybe more will come on as this gets up. So,
Hello?
hey.
Oh,
Everybody hear?
finally.
Yeah,
I'm here.
Canvas is, they've had trouble this at CMC with Canvas, with the whole Canvas thing. I guess a lightning strike took down some of the power poles that ran the network.
Oh yeah, I got an email about that.
Yeah, started firing the preserve too. So we got a couple of people, so maybe hopefully we'll get more coming on. But right now, I think Diana had a question on this compound right here. Is this right, Diana?
Well, I haven't even tried the question, but I'm just stuck on I'm having a hard time with this chapter, I guess.
Okay.
Yeah, me too. This chapter is extremely confusing.
Oh my God. On one, I literally did 21 tries.
Okay, the thing to look for is it a metal and non-metal or two non-metals or polyatomic ion? So you can see that's a polyatomic ion, right? SO4?
The AG.
That's SO4, 2 minus. That's one of your polyatomic ions from the chart. Silver has a +1 charge. So how would you name it? You said the name of the metal first, right?
Yes.
So it's silver. And then you name the polyatomic ion, which is what?
So
Look on the polyatomic ion chart.
sulfate, right?
You got it. That's it.
Silver sulfate.
That's a U. Silver sulfate.
So the problems I had trouble on, the Roman numeral one. So is it that I subtract? I got it, but
No, like if Roman numerals are only for the transitional elements. Transitional elements are these right here. These are your transitional elements.
oh.
Okay, those are the ones, but there's some that you don't use, like silver is always +1, zinc's always +2. Okay, so you don't have to use those for that one. But everything here you use a Roman numeral for. So if you're going to combine, let's say, iron and chloride, let's say if you had, where did I go here? Okay, iron, if I had this compound, how would you name it?
Iron chloride.
Okay, so there's iron, right?
Yeah, iron chloride, right?
And then chloride. And you have to realize iron is a transitional metal. So you have to determine the charge. You determine the charge.
Oh, okay. That's where you put the Roman numeral.
Right in here.
So it would be a 3.
It'd be a 3 because this is 3 chlorine's -1, and there's 3 of them. So that is -3. So chlorine iron has to be +3 to balance. So it'd be iron 3 chloride.
I'm just going, this is going at such a high rate. I'm nervous for midterms.
It is. Summer classes are extremely hard chemistry.
Yeah. So I don't know how I'm supposed to remember all this. That's my problem.
There's a lot to remember. Yep.
You did say that the midterm and the final are multiple choice. Am I correct, or did I mishear?
It'll be multiple choice. true, false.
Oh, okay.
Yep.
I'll be praying. I'll be praying for everybody and myself.
It's not an easy class. It's a lot of work, especially for a summer class. It really is.
Yeah, it is a lot of work.
Yep.
And I'm also taking anatomy, so that makes it a little.
Oh,
harder.
I took it last semester, and yeah, that was hard too, but luckily I got an A, so good luck to you too.
Last semester,
Yeah, I had it with Laura O'Brien.
I have Dr. Basu.
Oh, well, I don't know how the person is, but Laura was pretty crazy too.
It's a lot of work, a lot of labs.
Yep.
Oh, yeah, it is.
We have 2 quizzes every Sunday.
Oh, well, he sounds crazier than my teacher, so never mind.
All right. Other questions on that?
So you said for that one, when it comes to determining the name for the transitionals, we look up at the charges, right?
Yep.
Okay, I'm gonna write that down.
It's not always straightforward. Like if you had, how would you name that compound?
Isn't it iron oxide?
Well, iron, then oxide, and you realize iron's a transition metal. So tell me the charge
So
on
you
it.
have to put 3, the Roman numeral 3. It's crisscross, right? Or not for this.
Yeah, it's iron 3 oxide
Yeah,
because the charge has to be, yeah.
yeah, it's crisscross.
Yep. Okay, so Roman numerals are only used with transitional metals.
Okay.
There's a couple exceptions, like silver is always +1. It's not transitional. Zinc's always +2.
Silver's not a transitional metal, even
No,
though it's
even though it's silver and zinc, even though they're in the transition metal chart, silver is always +1, zinc's always +2. This, you don't have to put the Roman numerals for those because those are not transitional, even though they're in the transitional group. There's always exceptions.
okay. So silver is +1 and zinc is +2.
Silver is always +1, zinc is always +2. Let's see. Okay. I know I had a couple email questions too. One was on a light frequency, which you talked about. Let's do that before we start on the chapter. And then one was on the SPDF orbitals. So someone had a question on, it said a certain shade of blue has a frequency of 7.2 0 times 10 to the 14 hertz. And they want to know the energy. You know, energy equals h nu, which is frequency. So Planck's constant times frequency. Planck's constant, you can look up at 6.626 times 10 to the minus 34 joule seconds. And frequency we said was 7.20 times 10 to the 14 hertz. And hertz is per second. Same thing. So you do the math, and that comes out to 47.702 072 times 10 to the minus 20 joules. And then put that in the right number of significant digits and scientific notation. You're only good to 3 significant digits. There's your 3 digits right there. So 47.7, 4.77 times 10 to the minus 19 joules. That's like one we did last time.
Is that minus 19 or minus 14?
Minus 19.
Oh, okay.
Because this is 30, because this is minus 34, this is, and this was 14. So that gives you minus 20, which is right here. And then we move this decimal, made this smaller. So make this bigger by 1. So 4.77 times 10 to minus 19 joules. And there was another question on, let me get that out of the way. Yeah, no, on sapling and some of the books, they put the orbitals in different order. So in other words, if I had manganese, we put it as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d5. A lot of books in there, they'll rearrange it to put in numerical order, like 1s2, 2s2, 2p6, 3s2, 3p6. Then they'll put they'll put all the threes together, 3d5, then 4s2. It's the exact same thing. On my exams, we're just keeping that order, makes it easier. On sapling stuff, you might see them reverse the order like that. Some do it, some don't. I know it makes it a little confusing, but it's the same thing. It's just they put everything together, all the numeric ones together, numerical order, and then S, P, D, F in that order. Okay, so those are two of the questions before chapter 5. Then we have some more in class for chapter 6. We haven't done that yet, right? 3, 4, 5. Yeah, chapter 6 today.
No, I haven't done 6 yet.
All right. So we'll do 6, then I'll go back and answer the question on chapter 6 and post it to the email. And a couple other ones that were on there. Does that sound good?
Okay.
Or any burning questions? Any burning questions before we start chapter 6? Okay, I'll review. I'll go ahead and review. Is this still recording? Let me check. Make sure I'm recording before we start chapter 6. Yeah, I did get your email, Tara, and those are the questions on chapter 6. So we'll go over chapter 6, then we'll go over and answer your questions, okay? Does that make sense? Perfect. All right. All right, so chapter 6. Chapter 6 is chemical equations, reactions, all that fun stuff. Okay. So we write a chemical equation. Okay, let's go through this here. On the left side is our reactants, right side is our products. So if we have hydrogen plus oxygen goes to water, these are reactants, these are products. So reactants on the left, products on the right. Okay. What else do we have to do on this one here? So in writing chemical equations, we're going to learn how to balance the equation. Okay? That allows us to predict the ratios because everything happens according to a balanced chemical equation. Chemical equations don't mean anything unless they're balanced. And balancing the equation means you have to have the same number of elements on one side as the other side because you cannot create or destroy mass in a chemical equation. So let's take what we had up above, hydrogen plus oxygen goes to water. Okay. So on the left side, we have 2 hydrogens, right? H2. We have 2 oxygens. Okay. On the right side, we have 2 hydrogens, but only 1 oxygen. When there's no number here, that means it's 1. We never put a 1 as one of the subscripts. If there's nothing there, it's a 1. The only place you can touch when balancing a chemical equation is in front of the compound. You can never, ever, ever touch my subscripts, okay? You cannot ever touch this, touch this, touch this, or touch this, because then you change the compound or the element. Okay? You can never touch the subscripts. The only place you can put a number is in front, right here. That's it. So if I write this out again, hydrogen plus oxygen goes to water. Okay, we have 2 hydrogen, we have 2 hydrogen, left side, right side. We're good. We have 2 oxygen on the left. We only have 1 on the right. So we have to make that say 2. The only place I can put a number is in front of the compound. So I have to put a 2 right here. Okay, now that 2 applies to the water. So there's 2 water molecules. So H2O and H2O. That means I have 4 hydrogens and 2 oxygens. Okay, there's 2 water molecules. So I look at both of these, you can see there's 4 hydrogens total and there's 2 oxygens. So my oxygens are bounced out, now my hydrogens are off. So this, on the right side of my product side, I have 4 hydrogens. How do I make 4 on the left side? What do I put in front of this hydrogen right here?
2?
Did someone say 2?
Yeah.
Okay, put a 2 right there. So now I have 4 hydrogens and 2 oxygens. Here I have 4 hydrogens and 2 oxygens. Now I have a balanced chemical equation. And we're going to use those in the next chapter doing stoichiometry, doing lots of calculations with these. So you have to be able to balance chemical equation. Will be a bunch of practice today too. So that's a balanced chemical equation. Same number of elements of each type on the left as are on the right. That's what a balanced chemical equation means. Okay, so let's do burning of methane gas. CH4 plus oxygen goes to carbon dioxide plus water. Anytime you burn a hydrocarbon is just carbon and hydrogen. Burning means add oxygen. Everything burns in the presence of oxygen. Okay? There's only one thing that burns without oxygen, and that's thermoplastics, especially controlled explosives from the United States government. Let's see, okay, so everything burns in the presence of oxygen. If it's a hydrocarbon, it's always going to produce carbon dioxide and water. Okay, so let's balance this thing. When you have something by itself, like oxygen, we say that till the end. That just makes it easier for you. So if something's alone, like oxygen, like an element, like oxygen, we leave it. If it's hydrogen, we leave it till the end. So we leave oxygen to the end. So let's start balancing this. How many carbons on the left side? Someone give me a number.
1.
1, perfect. There's 1 carbon left. How many carbons on the right?
1.
1.
Got it. So carbon's good. How many hydrogens on the left?
4.
4, perfect. How many hydrogens on the right?
2.
2. So how to make that say 4?
You put a 2 in front of the H2.
Okay, so I can't do this, right? Make H4O, right? Okay, because you can't touch those subscripts ever. The only place you put numbers is in front of it. So that gives me 4. So my carbon's balanced and my hydrogen's balanced. Now let's balance the oxygen. How many oxygen on the left, on the right-hand side?
On the right side,
On the
Sure.
right side.
1.
No, how many oxygens?
3, isn't there?
2.
No, haven't heard it yet. I have 2 oxygens here
4.
and I have 2 oxygens here. So how many do I have?
4.
4.
4.
So how to make this side say 4? What do I put in front of the oxygen?
2.
2. There you go. Now we got a balanced chemical equation. Okay. And what we're going to learn is this tells us the number of moles of what's reacting. That's how we're going to, everything in chemistry is going to be in moles. And we're going to what that is in the next chapter. But that's what a balanced chemical equation is. It says 1 mole of methane plus 2 moles of oxygen are going to give you 1 mole of carbon dioxide and 2 moles of water. Everything's in a molar relationship. It's not in grams, not in mass, it's always in moles. So we can predict the ratios from these chemical equations. If we had, let's take another one. Let's say CH2N2. Get these right from your books, you can follow along. And that's going to go to nitrogen gas plus ethane, C2H4, ethine actually, C2H4, right? Okay. So let's get this out of the way. I don't want to confuse you with that. All right. So we'll leave nitrogen till the end. So let's balance carbon. How many carbons on the left?
1,
How many on the right?
2,
2. So how to make the left side say 2?
add a 2 before the C.
Yep, put a 2 right there. Okay, so now the carbons are balanced. Now we're going to save the nitrogens till last because this is a single thing. So let's do hydrogens. How many hydrogens on the on the left hand side now?
2,
No, how many hydrogens?
4,
4. There's 2 sets of 2, so there's 4 hydrogens. How many on the right hand side?
4,
So now our carbon and hydrogen are balanced. Let's look at nitrogens. How many nitrogens on the left?
4,
4. Perfect. So how to make this one say 4 on the right?
add a 2.
Add a 2. So let's look at it. We have 2 carbons on the left, 2 carbons on the right. We have 4 hydrogens on the right. I have 4 hydrogens. I mean, 4 on the left, 4 hydrogens on the right. I have 4 nitrogens. I have 4 nitrogens. And it's balanced. Right? It's not always this easy, but you have to be able to balance those chemical equations.
Dr. Howe,
Yeah.
I'm not following you. So are we adding the hydrogen? And so you have 2 CH2N2. So you have 2 on this side. I don't know if I'm asking the question right.
Okay. So I have 2. I have a CH, 2 hydrogens, 2 hydrogens. There. I have one carbon, 2 hydrogens, 2 nitrogens, right? That's what this says right here.
Yes.
Okay, and I have 2 of those. So how many total carbons do I have looking at both of those?
I have 4 of each, right?
I have 2 carbons, right?
2 carbons, yes.
How many hydrogens?
4,
How many nitrogens?
4.
Perfect. Same on the other side. I have N, 2 nitrogens, right? And I have 2 of those. And I have 2 carbons
Oh,
and
I
then 4 hydrogens.
see that. Okay.
Sometimes it helps to write them out a little bit. So again, 2 carbons, 4 nitrogens, 4 hydrogens. Same on both sides. Okay. So you gotta know how to balance chemical equations, pursue the rest of the stuff. So make sure this makes sense to you. We'll do another example here. Nitrogen plus hydrogen goes to ammonia. This is a Haber process, making explosives. Okay. So what are we going to do here? Let's pick nitrogen. How many nitrogens on the left-hand side?
2,
2,
2. So how to make the right-hand side have 2 nitrogens?
add a 2.
Add a 2. How many hydrogens now on the right-hand side?
5,
Not 5. There's 2 sets of 3. So 2 times 3, right?
6,
There's 6, right? Because NH3, nitrogen, hydrogen, 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 nitrogen, hydrogen, hydrogen, hydrogen. So 2 nitrogens and 6 hydrogens. So you multiply it because you have that many sets of them. Okay. So I need to have 6 hydrogens on the left-hand side. So what do I put in front of my hydrogen? Right there.
3.
3. That gives me 6. Perfect.
So that's what I was trying to ask you, multiply.
Right. Because there's sets of them. There's 2 groups of NH3. There's 2 groups of H2. So it's multiplied. Like 2 sets of 3. Or 3 sets of 2. Okay. And that's balanced. So if you were looking at molecules, this is, you could say like in the book it says here, it says 1,000 molecules. Let's just do 100, it's easy, right? So 100 molecules reacts with 300 molecules to give you 200 molecules of ammonia. So it takes 100 molecules of nitrogen, reacts with 300 molecules of hydrogen, because it's in a 1-to-3 ratio. Because if there's no number here, it's a 1. So it's in a 1-to-3 ratio. So 100 molecules of nitrogen react with 300 molecules of hydrogen, and you're going to produce 200 molecules of ammonia. That's what your equation's telling you. That's your balanced chemical equation. Okay, let's do another one. Keep us on track here. Iron plus oxygen goes to, what do I go to? Fe2O3. Iron 3 oxide. All right. Little trickier here. I'll show you a little trick I do. I know people don't like fractions, but I'll use fractions just for a temporary measure to get this. So how many moles of how many irons on the right-hand side?
1. Oh, sorry, I was looking at the list.
I'm on the right. No problem. So what did I put in front of the iron on the left?
1. Oh, 2.
2, right? So I got 2 irons on the left, 2 irons on the right. Now, this is an odd number and an even number. So I have 3 oxygens on the right and only 2 on the left. How do I make the left-hand side say 3? So what number times 3 times 2 equals 3? Okay, 3 halves, right? So I put 3 halves right here, because 3 halves times 2 equals 3. And that gives me, now you cannot have fractions in a balanced chemical equation. I'll get rid of it in just a second. But I just use those, because sometimes they get a little more complicated. So I just use these as an intermediate step to help me see it. So now I have 2 irons, I have 3 oxygens, 2 irons, and 3 oxygens. So now I'm balanced. So what I can do now to get rid of that fraction is I can multiply everything by 2. So I take this times 2, and I take this times 2. So I end up with 4 irons plus 3 oxygens goes to 2 iron 3 oxides. That's your balanced chemical equation. So I use the fraction just to get my numbers right. Then I get rid of the fraction by multiplying by the denominator here by 2. That gets rid of it. So I have to multiply everything by 2. So 2 times 2 is 4. 3 halves times 2 is 3. 1 times 2 is 2. And that's balanced. How many irons on the left on the balanced on this equation right here?
On the left,
On the left.
4.
4. How many on the right?
4.
How many
4.
oxygen? Perfect. How many oxygen on the left?
3.
No.
6.
Oh,
6.
that's 6.
Easy mistakes to make. Make them now. Don't make them on the test. So that's good. So 6 on the left. How many oxygens on the right?
6.
6. 3 times 2. Perfect. So it's balanced. Yep. So I will use fractions sometimes, but they're just an intermediate step. You cannot leave a fraction there. And I know that, but I'm just using it to get my numbers in the right ratio, then just multiplying it out, and I'll get the right equation that I want. Okay. So let's do another one. Does this start to make a little more sense now?
Yeah,
We go right from your book here. Okay, good. Because this is an important part. Copper plus KCl. All right. Potassium plus copper 2 chloride goes to copper plus potassium chloride. Okay, is that balanced?
No.
No. Perfect. So let's look at everything. Let's look at copper. How many coppers on the left?
1.
How many coppers on the right?
1.
Perfect. So copper is balanced. Chlorine. How many chlorines on the left?
2.
2. How many chlorines on the right?
1.
1. So what do you have to put in front of there?
A 2.
The 2 right here. Now that gives us 2. That gives us 2 potassiums on the right. So what did I put on this side?
A 2.
2. Are we balanced now?
Yes. No.
Huh?
Yeah.
Yeah. 2 potassiums, 1 copper, 2 chlorines. That's balanced. So that's our ratio, what we're going to use when they react.
So the 2 in front of the potassium on the right-hand side makes the chloride 2 on the right-hand side, right? I don't-
Yeah, this 2 here applies
Yeah,
to
it makes-
everything. It applies to the
Okay,
potassium
applies
and
to-
the chlorine.
Okay,
oh,
Right. Just
that
think of it this way.
I was curious
KCl,
about that too.
KCl. 2 groups of KCl. So there's 2 chlorines and 2 potassiums. So this number applies
Okay.
to every
both.
element in there.
okay.
Perfect. Good. Let's go a little bit trickier here. Let's do aluminum oxide plus carbon. I didn't leave enough room. Let's leave a little more room. Plus carbon plus chlorine goes to aluminum chloride plus something else, carbon monoxide. All right. So let's take a good look at this here. And let's save carbon for the last. So let's balance our aluminums. How many aluminums on the left-hand side? ALs on the left.
2.
2.
2. So what I put in front of the AlCl3?
A 2.
Put a 2 right there, right? 2 aluminums. So that changed my chlorines. So how many chlorines on the right-hand side now?
6.
6. Perfect. Everybody see what I'm getting? 6. 6 chlorines. So what do I put in front of this Cl2 here to make this say 6?
3.
Put a 3 in front of it. Okay, so my aluminum are balanced. My chlorines are balanced. My oxygens are not balanced. So what I have to put, I have how many oxygens on the left-hand side?
3.
3. How many oxygens on the right-hand side?
1.
1. So what I put in front of my carbon monoxide?
3.
3. Okay. So that changed my carbon. So how many carbons now do I have on the right-hand side? 3, right? I heard someone say 3. And then what I put for my carbon on the left-hand side?
3.
3.
3. Is that balanced? 2 aluminums on the left, 2 aluminums on the right. 3 oxygens on the left, 3 oxygens on the right. 3 carbons on the left, 3 carbons on the right. 6 chlorines on the left, 6 chlorines on the right. I'm balanced. You have to have the same number of elements on both sides of the chemical equation. So far, so good.
Yeah,
Okay, make more sense now.
yeah. I'm getting it a little bit
Okay,
more
good.
better.
Okay, good. A little more better. Perfect. All right, let's get another
Yeah.
reason from the book here. Let's do butane gas. C4H8 plus oxygen goes to carbon dioxide and water. All right. So remember, we save oxygen until the end because it's by itself. So how many carbons on the left side?
4.
4.
There's 4. Okay. How many hydrogens on the left side?
8.
8. So I put a 4 here also. Now, how many total oxygen are on the right-hand side? Look at it carefully.
8.
Not 8.
6.
10.
Oh, wait.
I haven't heard it yet.
12.
There you go.
6. Yeah.
There's 12. I have 4 and 2. I have 8 here, right? 8 oxygens. And I have 4 here. So I have a total of 12 oxygens. Okay. In the CO2, I have 8 because there's 4 of them. In the H2O, I have 4 because there's 4 waters. Okay. So I have a total of 12 oxygens on the right-hand side. So to make this side say 12, left side say 12, I put a 6 right here. So this tells me 1 molecule of butene combines with 6 molecules of oxygen, and it's going to produce 4 molecules of carbon dioxide and 4 molecules of water.
So for the one that says 4 H2O, we don't pay attention. We don't use the 2. We don't use the subscript. We just use the 4.
No, it's oxygen, not hydrogen. You're looking at the hydrogen. The substrate for oxygen is 1 because there's nothing here. That 2, this 2 here, this applies
Yeah.
to the hydrogen. So that gave us 8 hydrogen, which balanced 8 hydrogen. But that the substrates only apply to the element it's preceding it.
Okay, so since the subscript is 1 for the oxygen, there'll be 4 times 1. That's why you got 4.
Correct. Perfect.
Okay.
And the substrate for the hydrogen is 2. That's why 4 times 2 is 8 for the hydrogen.
Yeah, that makes sense now. I'm just gonna write the 1s just in case so I don't
It's okay.
overlook it.
Yeah, because everything that if it doesn't have any, it's always a 1. Okay, let's do one with polyatomic ions. Polyatomic ions, now this is how we balance with elements. When we have polyatomic ions, we keep them together in a group. So if we were to have, well, I'll do the one in the book here. Nickel nitrate, nickel 2 nitrate. So Ni, NO3 twice. Again, that's our polyatomic ion because there's 2 of those. Okay. Plus sodium hydroxide. Okay. Goes to sodium nitrate plus nickel 2 hydroxide. Make sure I got all that the correct way. Yeah. Okay. So there's your balanced chemical equation. We can figure out what it's going to go into. We don't use the substrate. The substrates determine the charge, how they're related. Okay, so when you have a polyatomic ion, we have 2 of them here. We have OH, hydroxide ion, which is a negative charge. So we have OH minus, and we have NO3 minus. Those are our 2 polyatomic ions. You can see they're on the same, we don't break them up. We balance those as a group. It becomes so much easier. I mean, don't balance as a nitrogen and an oxygen, or an oxygen and a hydrogen. Balance it as a group, but you have polyatomic ions, and they don't separate. Because you have OH here, and I have OH here. I have NO3 here, and NO3 here. So balance those as a group. So how many NO3 groups do I have on the left-hand side?
2.
2. So now I'm gonna make it say 2 on the right-hand side. So this is NaNO3, I put a 2 right here. That gives me 2 NAs, 2 sodiums, and 2 NO3s. It applies to both of those. So now the NO3 is balanced. Okay, that changed my sodium. I have how many sodiums now on the right-hand side? How many Na groups?
2.
2. I'm gonna make it 2 on the left-hand side. I gotta put a 2 in front of there. Okay. How many OH groups do I have on the right-hand side?
2.
2. How many OH groups do I have on the left-hand side?
2.
2. So I have 2 in front of the NaOH. So there's 2 H's, 2 H's. How many nickel groups do I? How many nickels do I have on the left-hand side?
Would it be 2?
No, not 2.
1.
Just 1. Because if there's no number in front of it, behind it's a 1. If there's no number here, it's a 1. How many nickels on the right-hand side?
1.
Perfect. You got it. 1 nickel on the left, 1 on the right. 2 NO3s on the left, 2 NO3s on the right. 2 NAs, sodiums on the left, 2 sodiums on the right. 2 OH groups on the left, 2 OH groups on the right. It's balanced. Let's do one more polyatomic ion one. Let's do, let me come with a good one. Let's do magnesium nitrate plus potassium phosphate. Okay. And that forms Mg, where am I at? 3, PO4 twice, and potassium nitrate. Okay, there's your equation. Take a good look at it. You know that you can see the NO3 groups on both sides. You can see the PO4 group on both sides. So you know you got polyatomic ions that don't break up. So balance them as a group. Makes it so much easier. So let's start with magnesium. How many magnesiums do you have on the left-hand side?
1.
Perfect. How many on the right?
3.
3. Because this 3 right here applies to what comes before it, the magnesium. So I put a 3 here. Now, that changed how many NO3 groups I have. So now look real careful at the left-hand side. How many nitrate groups do I have? NO3 groups.
6.
We got 6. Perfect. We have 2 groups and there's 3 sets of them. So we have 6. So I have to make this say 6 also. And I have 6. Now I have 6 potassiums over here. So how to make the left-hand side say 6 potassiums?
Out of 2.
Out of 2. Because it's K3 PO4. Is that balanced? Someone just say yes.
Yeah.
It's
Yeah.
balanced. 3 magnesium on the left, 3 on the right. 2 NO3 groups on the left, 2 NO3 groups, where am I at? I'm sorry. 3 magnesium on the left, 3 on the right. 6 NO3 groups on the left, 6 on the right. 6 potassiums on the left, 6 potassiums on the right. 2 PO4 groups on the left, 2 PO4 groups on the right. And we're balanced. And that's how you balance a polyatomic ion. Balance them by groups. Realize these groups all stay together. So it's so much easier to balance without saying, well, we have to balance the nitrogen and the oxygen. Just balance them as a group. All right, let's do one, well, let's a couple more with doing fractional ones. Let's do C2H6. So let's do C2H6 plus oxygen goes to, we should know this by now, CO2 and water. All right. So remember, oxygen is by itself, we leave that till the end. So how many carbons on the left?
2.
What's that?
2.
2, right? 2 carbons on the left. How many hydrogen on the left?
6.
6. So now I think 6 also. Now, how many oxygens on the right-hand side? Careful. How many oxygens on the right-hand side?
7.
How many?
1.
7.
7. Perfect. You got 4 here, right? 2 CO2s, and you got 3 here. You got 7 oxygens on the left-hand side. How do I make that 7? How do I make oxygen say 7? Put a 7 over 2 in front of the oxygen. Now we just get rid of our fraction. Multiply everything by 2. So our equation becomes, our balanced chemical equation. Again, you can't leave a fraction. The fraction is only there so we can help determine what our coefficients, our ratio is. And we multiply everything by 2 to get rid of fraction. So this is the correct answer. This is not the correct answer. The fraction is only there to help us in creating the balanced chemical equation. So 2 molecules of F-ethene plus 7 molecules of oxygen are going to produce 4 molecules of CO2 and 6 molecules of H2O. Cool. Let's do one more, maybe. Okay. I'll pick one from this book here. Let's try one that's right in the middle. Okay, aluminum nitrate, AlNO3 3 times. So it's what? Whoops, one more equation. Okay. Lose it. There you go. So aluminum nitrate plus sodium iodide. Okay, is going to go to the sodium nitrate. It's doing good. Oh wait, whoa! I'm combining 2 things here. Hold on, I wrote the wrong thing. That's why it wasn't working. Aluminum nitrate and calcium. Okay, goes to calcium nitrate and aluminum metal. All right, balance this one and then we'll go on to the next step. So how many aluminums? How many aluminums on the left?
1.
How many on the right?
1.
Perfect. We're done. No, just kidding. How many carbons on the left?
1.
How many carbons? I say calciums. I'm sorry. How many this is a parentheses. I know I don't write very neat. How many calciums on the left?
1.
How many on the right?
1.
Good. We're all almost there. So I'll get about balancing NO3s now. So how many NO3 groups on the right?
2.
2. Perfect. How many on the left?
3.
3. Got to make that say 3. You have to put a 3 over 2 in front of that. That gives me 3 NO3 groups. And then what I have to do to get rid of that fraction?
Multiply everything by a 2.
Everything by 2. That gives me 3 AlNO3 3 times plus 2 calciums goes to 2 calcium nitrates plus 2 aluminums. Right? So 3. What did I do? I did something backwards here. Okay. So we notice we have 3, 9. What did I do wrong? I messed up somewhere. What did I write on here? 3/2 to give me 3 nitrates. And we have to have 2 for that one. Okay. So now we got to balance the rest of this out. Okay. So there's I have how many NO3 groups on the left-hand side?
9.
9. So how did I calcium's balanced, NO3 twice. Dun, dun, dun. How did I do this? And that gave me 3. No, that gave me 9. Whoa. That's what I did wrong. Hold on. See, even I make mistakes doing these. Sometimes we get a little bit off. All right. So this is what we had. This is where we're at. I want to make 2/3. I put the wrong number here. I put the wrong fraction. Sorry about that. I want to have 2/3 because 2/3 times 3 gives me 2, right? I want to end. I have 3 NO3 groups on this side. I have 2 NO3 groups here. So I want the left side to say 2. So if I take 2/3 times 3, that gives me 2, which will balance, right? I put the wrong fraction. Does that make sense now? Because 2/3 times 3, the 3's cancel out 2. That gives me 2 NO3 groups and 2 NO3 groups on the right-hand side. Now multiply everything by 3 on the bottom because you multiply to get rid of that number. So multiply this by 3, you have 2 AlNO3 3 times plus 3 calciums goes to 3 CaNO3 twice plus 3 aluminums. Okay. We're still off by a little bit. We can fix that. Let me just double check that. Okay. So look at the numbers there. So how many aluminum is on the left? How did I end up? I'm still ending up wrong somewhere here. Times 3 times 3. I'm confusing myself here somehow. How come we're not balancing? 2/3. I want to make that say 2. So times about 2/3. Times everything by 3. And I'm still going to be off my aluminums. Why am I off my aluminums?
Is it because you're supposed to put the 2/3 in front of the before the parentheses instead of
You got to put it in front of the whole thing.
oh,
But somehow I'm getting. Oh, let me. All right. So AL. Maybe I shared the right one. AlNO3 twice. AlNO3. Oh, wrong compound. I copied it wrong. That's why I'm having trouble. All right, I copied it down wrong from the book. Let's start with the right way. AlNO2 3 times. AlNO2 3 times. Plus, my eyes are just going. Had a long day. Calcium, aluminum, plus CaNO2 twice. CaNO2 twice. All right, so let's balance our aluminums. One on each side, right?
Yeah.
We have one calcium on each side. Now we have 3 NO2 groups on the left. I want to make it say 3 NO2 groups on the right. Okay, so this is divided over 2. So this, let me put my little different color here. So if I put 3 halves, okay, that would give me 3 NO2 groups. Then multiply everything by 2 to get rid of the fraction. So we have 2 Al NO2 3 times plus 2 calciums goes to 2 aluminums plus 3 CaNO2 twice. Okay. So we've got okay. We're good. Just one little change. All right, so look at our equation. How many aluminums on the left?
6.
How many aluminums on the left? Remember, right here, only 1.
2.
So 2 aluminums on the left. How many on the right?
2.
2. Perfect. So aluminum's good. How many NO2 groups on the left?
3.
No. 2 groups of 3, right?
6.
6.
Right. So there's 6 NO2 groups on the left. How many on the right?
4. Is it? Yeah.
No.
6.
You have 3 groups of 2, right? So how many NO2 groups on the right?
6.
6. So those balance. So everything balanced there. How many calciums on the left?
2.
How many calcium on the right?
3.
Okay, so calciums don't balance. So how to make the calciums balance? We change this to a 3.
3.
And that's it. They're not all real straightforward. However, it's the right equation now. Okay, so now we got 2 aluminums on the left, 2 aluminums on the right. We got 6 NO2 groups on the left. We got 6 NO2 groups on the right. We got 3 calciums on the left. We got 3 calciums on the right. That's probably one of the harder ones to balance. Okay. And we're also going to deal with equations that have symbols behind, underneath the lens. We'll have like a subscript S or an AQ or an L or a G. Okay. If it has an S, it means solid. If it has an AQ, it means it's in an aqueous solution. Like if you take table salt and put it in a glass of water and mix it up, you have sodium and chlorine ions in solution. Those are AQ. L is a liquid. Water is a liquid. So it's water is an L. G is for a gas. So solid, aqueous solutions, liquid, and gas. Those are what our subscripts mean. And we're going to be using those in just a little bit here. Now, there's 4 types of reactions you need to know. There's decomposition. Okay, there's combination. There is single displacement and double displacement. Okay, those are the 4 you need to know and be able to identify. So it was first one was a decomposition. Decomposition is one thing going to 2 or more. So A breaks up into B plus C. That's a decomposition. One thing breaks up into more than one. One thing breaks up into 2 or more. Okay, that's a decomposition. Okay, a composition reaction or combination or synthesis reaction is where 2 things combine to form 1. So decomposition breaks it down. One thing goes in 2 or more. Combination where 2 things combine to form 1. We have a single displacement and a double displacement. Single displacement reaction is when one thing, A, and we have a compound BC. And this A goes here and kicks off that B, and this becomes AC plus B. So one thing displaces another. So the A kicks off the B, and now it goes in the solution, and the A binds to C. So one thing is being displaced from the compound. Double displacement, two things being displaced. You have AB plus CD, okay? You end up with AD plus CB. Okay? Where both of these, the A has now combined with the D, the B or the C has now combined with the B. Remember, the metal always comes first. We did our nomenclature before. Okay? So both things have been replaced. Okay? Always has the metal first, so the A has to start it and the C has to start it. So the first one has to be an A, first one has to be a C when we're dealing with that. So decomposition, combination, single displacement, double displacement. Does that make sense?
Yeah.
So far, so good. All right, so let's give you some examples here. So classify, we'll go further, we'll get them from the book. How about PB? NO3 twice. So lead nitrate plus potassium iodide goes to NO3s and PbI2. The imbalance it for you. Okay, is that a combination? Is that a decomposition, combination, single displacement, or double displacement reaction? What type? That looks funny here. That's an N.
Yeah, I got confused with that one.
Yeah,
Like
I'm
a
right.
double displacement.
That's what should be there. Okay, combination, decomposition, combination, single displacement, double displacement.
Double displacement.
Double displacement, you got it, perfect. Okay, the lead has combined with the iodine, the potassium has combined with the nitrate. So two things have been displaced. That's a double displacement reaction. Okay, let's do 4Al plus 3O2, 4 aluminums plus 3 O2s goes to 2 Al2O3. What type of reaction is that one?
I'm sorry, what was the,
What was what?
I'm sorry, what was the first,
First
what
is
was
a
the
double,
first one?
first is a double displacement reaction. Because
Okay,
they switched at both places. The lead's combined with the iodine, and the potassium is combined with the nitrate.
okay, thank you.
Okay, no problem. Okay, what's the second one? So this is double displacement reaction. Okay, what's the second one?
Is it single?
No, not single, nothing's been displaced.
Would it be combination?
Combination reaction, two things combined to form one. Combination reaction. And then hydrogen peroxide goes to 2 waters plus oxygen gas. What's that one?
Displacement.
What's that?
Single displacement.
Not a single displacement. It's one thing Going to 2 or more.
Decomposition?
Decomposition. This is a reaction that occurs when you're by hydrogen peroxide in the store. You know it's in a brown bottle, and you know it's not a very tight. It's got a seal that doesn't seal all the way on it. Because when hydrogen peroxide is exposed to light, this reaction occurs and it forms oxygen gas. And if you have a sealed container, light's being exposed, you have a bomb because you're building up gas inside a pressurized container. It's going to eventually go off. That's why hydrogen peroxide is always sold in a dark bottle, so the reaction doesn't occur, breaking down into oxygen. And Fe plus tin chloride goes to tin plus FeCl2. Okay, this one is a
Zero displacement?
single displacement reaction. Perfect. Okay, so double displacement, both things are being switched. In a combination, 2 things form 1. In a decomposition, 1 thing forms 2 or more. In a single displacement, 1 thing is being switched out. Those are the 4 types of reaction you need to be able to identify. Okay, questions on that?
No.
Perfect. All right, next one was predicting products with metals. There's just the different types of reactions that we just did. And then you're just going to balance them. So if aluminum and chlorine combine, aluminum plus chlorine. Okay. Now, aluminum has, look at the periodic table, you know, aluminum has a +3 charge. You know, chlorine has a -1 charge. So you're going to have to combine to form the correct charges. So you get AlCl3. Remember the crisscross rule? So that's how metals and nonmetals are always going to combine. They're going to combine according to the charges, so they have to be neutral. Aluminum has 3 positive charges. Chlorine has a -1 charge. So for every aluminum, you have to have 3 chlorines that bind to it. So AlCl3. So now that's not balanced. Okay, most students are going to just put AlCl2 because we're right across, so it balances. You can't do that. You have to balance the charges. Now we got to balance the equation. Okay. So if I put a 2 here, I can put a 3 here and a 2 here. And that's balanced. 2 aluminums and then 6 chlorines. Okay, so when the metals combined, you need to be able to predict what they are and then balance the equation. If we have magnesium plus chlorine gas, what's that going to form? Now you tell me this time. What's the charge of magnesium? Look at your periodic table.
+2.
+2. What's the charge on chlorine? It's in row group 7A, right? So it's -1. Perfect, -1. So do the crisscross, it's going to be MgCl2. So that's how you write. Now you have to balance the equation. And in this case, it's balanced. Okay, that was an easy one. But let's combine. Let's do magnesium again and nitrogen gas. Okay, so we're going to combine magnesium and nitrogen. What's the charge of magnesium? We said it's +2, right? What's the charge on nitrogen?
-3.
-3.
-3, perfect. So do you crisscross? That's Mg3N2. That's what forms. You can't just write Mgn2 because it doesn't form like that. Ionic compounds have to be combined by charges, like we went over before. Okay. So to balance this, we put a 3 here, and we're balanced. So when our metals combine with the nonmetals in a reaction, we have to make sure we put the right subscripts for the equation to balance the charges, and then we balance our equation by putting numbers in front of the compounds. What do we got here? All right, it says predict the, let's do another from the book, we'll move on to combustion reactions, if you've done some of those already. So let's say we combine, what are we after here? Potassium and sulfur. So let's combine potassium and sulfur. So it's going to be Ks. But what are the subscripts now? Potassium has what charge? You guys don't know that yet.
Is it +1 for potassium?
Potassium's +1. Yep, +1. And sulfur is?
It is,
-2.
yeah, -2.
Perfect. -2. You got it. So it's going to be K2S. That's what combines. Okay, now balance your equation. So you use your charges to determine your subscripts because it has to balance. Now you balance your equation. The compound has to be neutral. So how do we balance this equation? What will we do?
Add a 2 before the K on the left side.
You got it. Perfect. That's it. You guys got this. Good job. All right, we're talking about combustion reactions. Combustion reactions are reacting with oxygen. That's what combustion reaction is. Burns in the presence of oxygen. So let's do, here's what I want to do. C8H18. Let's use octane. That's what you burn your car. Octane gas plus oxygen, and your car produces carbon dioxide and water. All right, so there's your combustion reaction. And again, we're going to kind of review this again. So let's balance this. How many carbons on the left?
8,
How many on the right?
1,
So what do we do?
it's 7,
Not 7,
but 8.
8.
8.
Yeah, because it's 1, 8 times 1, my bad.
Yeah, that's all right. That's good. Like I said, make the dumb mistakes now. Make it when you're working with me. Then you won't make them on the test. That's why it's important to interact and talk. Because I'd much rather make the mistakes now than make them on the midterm. So 8 carbons. Okay. How many hydrogens on the left?
18.
18,
Perfect. So what do I put in front of the water?
9.
9. Perfect. You got it. Now we add up our oxygens. So now be careful. How many oxygens on the right-hand side?
9.
No.
1,
11.
No. Keep going.
oh, wait, there you go.
25.
There you go. Perfect. You got 25 oxygens over here. You got 8 times 2, which is 16. 9 times 1, which is 9. Very good. 25 oxygens. Now, how to make this? I say 25. (25/2). And then we multiply everything by 2. So we end up with 2 octanes plus 25 oxygens goes to 16 carbon dioxides and 18 waters. Okay. So 2 molecules of octane are going to burn up 25 molecules of oxygen, and they're going to produce 16 molecules of carbon dioxide and 18 molecules of water. when your car runs. So we burn up a lot of oxygen, we produce a lot of CO2. And CO2 is a greenhouse gas. And that's what we're trying to limit. Okay, so that's your balanced combustion reaction. And you can do that, you can do any of the other ones.
Aren't the carbons 8, or am I confused on the right-hand side?
What's that?
On the right-hand side, aren't they 8? Because this was
On the
the
right-hand
number
side.
6. Yeah, the number 16, wasn't that the oxygen molecules? And 8.
Right, there's 16
the
oxygen
carbon.
molecules.
Yeah, and so down
Correct.
the bottom, it would be 8 carbon molecules with the 2 oxygen molecules, right? Or the number of
Right, and then we multiply everything by 2 to get rid of this fraction here.
Oh, okay.
So that went to 16, that went to 18. And then this went to 2. You multiply everything by 2 to get rid of that fraction. So you can't have a fraction. Does that make sense?
Yes.
Okay, perfect. Okay, let's do one more. It says write a balanced equation that describes the combustion of magnesium. Okay, so that's a typical question. Write an equation that describes the combustion of magnesium. So write down magnesium plus, and means burning in the presence of oxygen. Combustion means oxygen. Oxygen is always O2. And what does magnesium and oxygen form when they combine? You're going to put magnesium and you're going to put oxygen. What's the charge of magnesium? Look at your periodic table.
+2.
It's +2,
What's the charge on oxygen?
-2.
-2. So it's 1 to 1, right? So it's MgO. So there's your equation. Now, how do we balance it?
Add a 2 to the left, to the right side,
Okay.
and then add a 2 on the right side.
You got it. Perfect. Then you got a balanced equation. So now you can write a chemical equation. If I just tell you a metal and say it combusts, you can tell me how to do it. How it combines with the balance of charges and balance equation. Perfect. All right. Reactions in aqueous solutions. We said things dissolve in water. Those are salts. So say we had potassium sulfate, K2SO4. Okay. So K2SO4 is solid salt. And then it goes to K plus and SO4 2 minus. And there's 2 potassiums as it goes. Because it breaks apart by the metal and the polyatomic ion. And these are aqueous, AQ. That means they dissolve in solution. Potassium sulfate dissolves in, just like sodium chloride goes to Na plus and Cl minus. Okay, so those are their ionic equations. That's how to write an ionic equation. You have to get a little bit tougher here too. But let's say aluminum nitrate dissolves in water. Aluminum, Al, and nitrate. Nitrate is NO3 3 times. Okay, so aluminum nitrate, we're going to dissolve in water, right? It's going to form, what's the charge on aluminum? Look at your periodic table.
It is +3.
3 plus 3 plus 3. We got 3 of these, NO3. What's the charge on nitrate? Look at the polyatomic ion chart. What's the charge on NO3? If you look at your polyatomic ion chart, I don't have one in here. Right here. NO3 is -1. That's where you're going to get it from. There, all right. So 3 -1 charges and a 1 + 3 charge. That's how it dissolves in ionic equation. And this is a solid, and this went to aqueous, which means it dissolves as an ion in solution. Okay. Now you have to be able to predict what's going to dissolve and what's not going to dissolve. And there's a bunch of rules for that. But I put in a chart for you up in the beginning here. These are on your data packet. The polyatomic ions, this little chart. So anytime I give you something, you'll be able to tell me if it's soluble. So an S means it's solid. Aqueous means it dissolves in solution. So S is what we call a precipitate, which means it's insoluble, does not dissolve in water. AQ means it dissolves in water. If I put calcium iodide, you look at calcium iodide, that dissolves in water. So whenever we give an equation, we're going to have to write net ionic equations here. This will tell us what dissolves. I mean, there's a bunch of rules, and the rules are up here. You know, alkali metals, lithium, sodium, potassium, ammonium, okay, NO3 and chlorate, perchlorate, or acetate are always soluble. But if you just look at the chart here, you'll be able to find the two. So if you look at the chart, if I say potassium sulfide, so potassium sulfate, is potassium sulfate soluble or insoluble? Find potassium
It's soluble.
and find sulfate. Right there. It's soluble. Now you can tell whatever we're given, you can tell me it's a solid or insoluble, right? Just look it up on the chart. Okay. Iron 2 chlorate. Look at iron 2. You find chlorate. Iron 2 chloride, sorry, would be aqueous, would be soluble. Iron 2 carbonate is a solid. So whatever we're given, we can tell just by using this chart what is soluble, what is insoluble. Makes it very simple. So let's go back and keep that chart handy in our minds. All right, so use the chart to determine if sodium acetate is soluble or not. So someone look at the chart, tell me sodium acetate, C2H3O2. Soluble or insoluble? Should be on the chart, right? Sodium, and then acetate, right here. Soluble and insoluble. What do we got? Look at sodium, look at acetate. What does that say? That says it's soluble, right? Is everybody understanding how to use the chart here?
Yeah, I do
Yeah.
understand how to use it. I was just pulling it up.
Oh, okay, okay. Perfect. So sodium acetate would be soluble. Let's do another one, Fe. Iron 3 chloride. Soluble and insoluble. Everybody see the chart?
Soluble.
Soluble, okay. Because it's aqueous, right? And calcium sulfate, CaSO4. Soluble and insoluble.
Insoluble.
Oh, perfect. Okay, so just use the chart, just find the intersection of the two and you know what's soluble and what's insoluble. So when we mix, we have different types of formulas. We have molecular formulas, which are the molecules. Then we got ionic formulas. Then we're gonna have a net ionic equation. So let's do an example and I'll show you exactly what we mean. So if we're gonna take this, we're gonna use that chart here just a second too. So keep that chart pulled up. Let me just sort of do it so it's clear. All right, so say we have lead nitrate. Okay, and I'm going to mix that with sodium iodide. Okay, and it's going to form double spacing reaction. It's going to form PbI plus Na NO3. Okay, and the I is going to, this lead is 2, so this has to be a 2 there. Okay. So now first thing we do is balance that. We have 2 NO3 groups, so I put a 2 here. And we have 2 sodiums, so I put a 2 here. 2 I's, and does that look balanced, everybody?
Yes.
Okay, so for your midterm, I'm going to ask you to write these 3 types of equations. This is your molecular equation. Okay, so the first step is write your I can't spell molecular. Okay, molecular equation. From this, we're going to write our ionic equation, which means we break down everything into ions. If you look at the chart, you'll see lead nitrate is soluble. So Pb 2 plus 2 NO3 minus. Okay, that breaks in ions. You look at sodium iodide, you'll see that is soluble. So we have 2 Na plus 2 I minus. Okay, both those break into ions. Okay, and it forms PbI2. PbI2 is insoluble. This is a precipitate. That's a solid. Look at the chart. And then this combines to 2 Na plus 2 NO3 minus. So the first one is your molecular formula. Your next one is your total ionic equation. And again, there's going to be 3 of these. You need to be able to write all of them. Total ionic equation. Okay? So your molecular equation is your balanced chemical equation. Then we break it in ions. Everything that breaks in ions, everything that is aqueous on that chart breaks into ions when it's dissolved in water. So lead nitrate breaks into lead and nitrate. Sodium iodide breaks into sodium and iodide. Lead iodide is insoluble. It's a solid. It does not break apart in water. It forms what's called a precipitate. And then sodium nitrate breaks into sodium nitrate. We good so far? And we can write those 2 equations. Then the next one is your net ionic equation. Okay? If you look at this, you'll see there's exact same things on both sides. There's 2 sodiums. There's 2 sodiums. There's 2 nitrates. There's 2 nitrates. Those are what's called spectator ions. Those are the ones that the same both sides. They don't participate in the reaction. Okay? So we can eliminate the spectator ions because they're not doing anything. So your net ionic equation is what's left over. Pb2 plus, again, this is aqueous in solution, plus 2I minus, and again, aqueous, goes to PbI2 solid. That is your net ionic equation. The net ionic equation is this equation minus the spectator ions. This is the same on both sides. Okay. So the molecular equation is just like we've been balancing equations. Your ionic equation is how it breaks into ions in solution. Your net ionic equation is minus the spectator ions. Your total ionic equation minus the spectator ions. And that becomes your net ionic equation. I guarantee you see that on the midterm. You have to write all three of them. Okay. And
What's
let's
next to the, I'm sorry, what's next to the PB2 plus, the parentheses? Is that
AQ.
a,
AQ.
yeah, I couldn't read it.
Yeah, AQ. That's an AQ also. Means aqueous. They're, all these are aqueous. We put a little AQ there, little AQ there, AQ there, AQ there, and AQ here, and AQ here. They're all aqueous in solution. I know
And so the PBI2 is soluble?
solid. That's a precipitate.
Oh, there you go.
Because if you look on the, if you look on all that, look on the chart, I'll bring it back up here. See lead to, where's iodide? Lead to iodide right here. That's PBI2. And that's a solid. Look up all the rest of them, they're all aqueous, they're all precipitates.
Okay.
Okay? Let's do another one of those since people tend to miss that on the midterm. Okay, let's do, I want one that's gonna work. Okay, let's do silver acetate. So silver, AgC2H3O2, silver acetate. Plus, what else you want to put in there? How about barium chloride? BaCl2. Okay. You should be able to do that from the names I just gave you. Write those compounds, silver acetate and barium chloride, and then double displaced reactions. You would form barium. So this, the plus and the minuses switch. This goes to this goes to this. So you get AgCl plus Ba acetate, C2H3O2. Great. Now you got to balance it. You got two chlorines. So you got two chlorines, two silvers, two silvers. What am I doing? Oh, barium acetate. This is twice. The parentheses around there. I think that's +2 -1. So two chlorines, two silvers, one barium, two acetates. Good. We're balanced. Okay. So that's our molecular equation, right? Everybody can do that right now. Any questions on that one? That's just your balanced chemical equation. Any questions with that so far?
No.
Okay, so that's your first step. That's your molecular equation. Then we have our ionic equation. We're going to break everything apart. So we have 2 Ag plus because of this 2 right here. We have 2 acetates, C2H3O2 minus. We have 1 Ba2 plus and 2 Cl minuses. Okay. Then we have AgCl plus Ba2 plus 2 C2H3 O2s. Okay, if you look on the chart, you'll see the silver acetate is soluble. We'll see barium chloride is soluble. We'll see barium acetate is soluble. Silver chloride is a solid, it's a precipitate. Okay. Everybody else see that on the chart. Silver acetate, barium chloride. So let's look at silver acetate, in case you don't believe me. Here's silver. And here's acetate. That's supposed to say, that's a mistake in the chart. That's supposed to be aqueous right there. Son of a gun. Oh, that's aluminum. Okay. Silver acetate, that should be aqueous. That's why we broke it up. I'll make sure and tell you that if it's on there. And then barium, what was the other one? Barium. Barium chloride. Wasn't a good example. Barium chloride is right here. That's aqueous. And then AgCl, silver chloride, that is a solid. There's your precipitate. So looking at that, assuming that was the right way on that one's just blew it off. These are, so what's our spectator ions? Looking at this, what's your spectator ions? What's the say on both sides? We have barium 2 plus, barium 2 plus. We have 2 acetates, we have 2 acetates. So your net ionic equation is Ag plus Cl minus goes to AgCl solid. And these are aqueous. So this is your molecular formula. This is your total ionic equation. This is your net ionic equation. And that's how you predict it. Okay, let's see. Maybe one more, you guys got this one. So it's a magnesium bromide. And potassium phosphate. Okay, that's what your question is saying. It's going to say on your matrix, combine, not these exact ones, combine magnesium bromide with potassium phosphate. Okay, give me the molecular balance equation, give me the total ionic equation, give me the net ionic equation. Be 3 different steps to it. Okay. You should all be able to do that now because it's going to combine a bunch of things we've been learning about. So magnesium bromide. First, we have to write magnesium bromide. So what's magnesium bromide? Magnesium is Mg, right?
And
Okay.
negative,
Bromide's
positive 2.
positive 2, very good. And then bromide, which is what?
-1.
You have bromine, and it's -1. Okay, so do your crisscross, MgBr2. That's magnesium bromide, plus potassium, which is K, phosphate. Remember, ATE ending, those are polyatomic ions. IDE is your elements, like bromide. ATE or ITE is your polyatomic ions. So look at phosphate, and it's K, potassium is +1, phosphate is -3. Do your crisscross, K3PO4. So now you got magnesium bromide and potassium phosphate. And you know you're gonna have a double displacing reactions when you're reacting to salts. Okay, so we're gonna have magnesium phosphate. So the positive part of one and the negative part of the other, magnesium phosphate. Mg's +2, phosphate's -3. So this is going to be Mg3PO4 twice, plus potassium bromide. Okay, potassium's +1, bromide's -1. So from those words, you should write that equation. Once you have that equation, you have to balance that equation. Okay, we balance it by, there's 3 magnesiums on the right, we put a 3 here. That gives you 6 bromines, so we'll put a 6 right here. There's 2 phosphates, so put a 2 there, and 6 potassiums. So 3 magnesium, 6 bromine, 6 bromine, 6 potassium, 2 phosphates, 2 phosphates. That's balanced. So this is the first step. This is what you give me as your molecular equation, molecular balance equation. Then the next one you're going to look at, okay, is going to be your total ionic equation. The total ionic equation breaks down into, you have 3 Mg2 plus 6, yes, I'm sorry, plus 6 Br minus. Okay, probably break down. You got your bromine ion, which is -1, right? Plus 6 potassiums, plus 2 phosphate groups. Okay. That's the left side. Okay. Now the right side, you have to whether it's going to form precipitated or not. Look at the solubility chart. Is magnesium phosphate a solid or aqueous? Okay. So magnesium phosphate
Solid.
is a solid, so it does not break apart in ions. Look on your solubility chart, Mg3PO4 twice. Plus 6 potassiums, because KBr, look at KBr on the solubility chart. What is that for? Is that solid or aqueous? Turn this off.
Aqueous. Potassium bromide, right?
Potassium bromide.
Yeah, it's aqueous.
It's aqueous, so it goes to 6 potassiums and 6 bromide. So the only one that's a solid is this magnesium phosphate. So now this is your total ionic equation. Okay. So you got your molecular equation, your total ionic. Now we look for our spectator ions. What are our spectator ions? Where are they? The ones that are the same on both sides.
6 Br negative.
6 Br negative. 6 Br negative. What else?
6K plus.
Perfect. 6K plus, 6K plus. Those are your spectator ions. So now our net ionic equation is going to be 3 Mg2 plus 2 PO4 3 minus goes to Mg3 PO4 twice. And this is a solid. And these are both aqueous. These are just ions in solution. Okay. So those are from what I gave you, from magnesium bromide reacts with potassium phosphate. You should write the molecular equation, balance it, the total ionic equation, and the net ionic equation. Be able to identify spectator ions. Okay. Does that make sense?
Yeah.
All right, perfect. And the last section is your acid-base neutralization. We're going to react an acid and a base and neutralize each other. It's just like what we've been doing. Same type of reactions. I'll give you an example. One really, it's simpler than the other one. We take a strong acid. Let's take a strong hydrochloric acid, HCl. React it with a strong base, sodium hydroxide. We get our salt, double displacement reaction, so I did before. The positive combines with the negative, negative combines with the positive, plus water, H2O. So whenever you get a neutralization reaction, we have an acid and a base, you end up with a salt and water. Because this combines here, and this positive combines here. And HOH is H2O water. Okay. So if we have our let's do a balanced equation. We have sulfuric acid, H2SO4, plus sodium hydroxide. Okay, we have a double displacement reaction. So we're going to form water, H2O, plus sodium sulfate, and A2SO4. So then we have to balance that. This is going to be our molecular equation, just like we did before. We said now it's an acid and a base. So we put a 2 in front of here. And where are we at? 1SO4, 1SO4, 2 hydrogens, 1 oxygen, 1 oxygen. We're good. That should be balanced, right? Looks good. Looks good to me. So there's your molecular equation. And then your ionic equation. H2SO4 is 2 H pluses plus SO4 2 minus. Because acids release hydrogen. Okay, then 2 Na pluses and 2 OH minus. Okay. Everything breaks into ions on that side. Water does not break into ions. So waters are liquid. Okay, plus 2 Na plus SO4 2 minus. All right, so now we've got, just like before, we got our total ionic equation. What are the spectator ions?
SO4 2 negative.
Got it. What else?
2Na.
2 Na plus. So our net ionic equation is H plus OH minus goes to H2O. Okay, all neutralization reactions are going to form water. They're going to neutralize. The acids and the bases neutralize each other. And you do an ionic, our net ionic equation, just like we did before. And it forms a salt and water, and salt is soluble. So it forms your ions. So it's the exact same thing we've been doing. Okay, it's just using an acid and a base. All right, and that is the end of chapter 6. Now, there were some questions for chapter 6 here. Let me pull those up real quick here. Don't need that. All right. It says some of your homework ones. It says complete and balance a precipitation reaction, including physical states. Okay, so let's do that. And this says barium nitrate. So it says Ba, this is like just like I've been doing, NO3 twice, aqueous, plus copper sulfate, copper 2 sulfate, aqueous, goes to. Right. It's going to form barium sulfate. That's aqueous, AQ. SO4 and copper 2 nitrate. Okay, and that's right. So here's our two combinations. Now we have to balance it and we have to tell them whether they're aqueous or soluble. So for our products, you have to look up. You're given that these two are aqueous. So look up Ba, barium sulfate. Is that solid or is that aqueous?
Soluble.
Solid. Perfect. And
Solid.
copper
The S
nitrate
is
is
solid.
copper nitrate is solid.
No, sorry, I was talking to myself.
Oh, okay. It should be aqueous, right? Okay. So that's your molecular equation. Is it balanced? 2 nitrates, 2 nitrates, 1 copper, 1 copper, 1 SO4, SO4. Yeah, it's already balanced. So we're good for the first one. We got that. The other one looks like you already filled that one in too. Complete and balanced molecular equations for the reaction. Okay, so the question at home where it says complete and balance a molecular equation for the reaction of aqueous chromium 2 bromide and aqueous sodium carbonate. Okay, so it gives you aqueous chromium bromide, which is CrBr2, and sodium carbonate, which is Na2CO3. That's what it gives you. And it says those are both aqueous. So AQ, AQ. What's it going to form? That's the question. So what does it form? And are you give a precipitate, or are they soluble? So again, you divide them into the positive side, the negative side, and you just switch them. So the chromium switches with the CrCO3. Both of those are +2 and -2, so that switches there, plus NaBr. Each one of those is +1 and -1. So there's your equation. Now you have to balance it. 1 Cr, there's 2 Brs on the left, make that 2 Brs here. There's 2 sodiums, 1 carbon, 1 carbon, that's balanced. Now look up on your chart. Is chromium carbonate soluble or insoluble?
Is the S a solid or?
Right, that's a solid.
So it's solid.
So this is a solid. That's a precipitate, and this is aqueous, if you look it up on the chart. Okay, that's the molecular equation. Now, it says also enter the balanced net ionic equation. So to get that, you have to do the total ionic equation, which is Cr2 plus 2 Br minus plus 2 Na plus CO3 2 minus goes to CrCO3, that's a solid, plus 2 Na plus 2 Br minus. And then you look for the spectator ions. Spectator ions, you just take it and you get rid of both sides. So what's our spectator ions?
2 Na plus.
2 Na plus.
2
And
bromide.
2 Br negative.
2 pounds. Perfect. So your net ionic equation is what it asks you for is Cr2 plus aqueous plus CO3 2 minus aqueous goes to chromium carbonate, solid. That's your net ionic equation. The net ion equation is just the total ion equation without the spectator ions. Okay. So that was a CR. And we did another one here. It says the molecular equation for, wait, any questions on that one? Okay. Go to another one. These are real good examples. These are perfect examples. So iron 3 nitrate, FeNO3. So FeNO3, iron 3, plus lithium hydroxide. And these are both aqueous. AQ, AQ. Goes to, write the molecular equation. So you should be getting the hang of this now. So the positive, divide in your positive and negatives on both sides. And then switch them. So you end up with iron hydroxide. And it's iron 3, so it's FeOH3 because Fe has a -1, OH has a -1 charge, plus lithium, and it combined with nitrate. There you go. Now balance it. There's 3 OHs, so you got to put a 3 here. It gives you 3 lithium, so you got to put a 3 here. That's an L. And 1 iron, 3 NO3, 3 NO3s, 3 lithium, 3 lithiums, 3 OH, 3 OH. It's balanced. Now you got to tell me, is this one here aqueous or solid? And is this one here aqueous or solid? So you have to look that up on the chart. So look up iron 3 hydroxide, FeOH. Is that solid or aqueous? Which one is it? So I'm looking on that solubility chart. Look at Fe3 and hydroxide. Go back. Whoa, how do all these get blank? Okay, iron 3 is right here. Hydroxide is right here. So where do those two meet? Right there. It's solid. Well, where'd my... Right. This computer's been acting funny lately. Is this on my right? I don't know why it is doing that. It just erased everything. Okay, so we had, I'll just remember what we had. We had Fe, NO3 3 times plus LiOH, and we had FeOH3 plus lithium nitrate. And we balance this with 3 OHs, 3 Lis. So 3 L and 3 Lis, 3 NO3s, 3 NO3s, 3 OH, 3 H, 1 I. Okay, and we said this was a solid and lithium nitrate is an aqueous solution. Okay, so this is our balanced molecular equation, and it wants it says enter the balance, okay, molecular equations, we did that. And the other part of the question was enter the balanced net ionic equation for the reaction, okay? So you would have Fe3 plus, and we know it's 3 plus, not 2 plus, because there's 3 NO3s, and each was minus and has to be neutral. plus 3 NO3 minuses plus 3 Li plus 3 OH minus. And that goes to FeOH3 because that did not separate, plus 3 Li plus 3 NO3 minus. So what are the spectator ions? Someone tell me.
3 and O.
It'd be NO3, right?
Yes.
3 of those, and what else?
And the 3 lithium.
3 lithiums. So your balanced net ionic equation is Fe3 plus 3 OH minus goes to FeOH3, which was a solid. There's an H right there. And these two are aqueous. Okay. I'm trying to look at the other one she sent in here. Looks like we got most of them. Okay. Questions on that one? Let's pick another one here. Okay, so write the net ionic equation for perchloric acid, HCl4. So let's go with H. Oh, okay, we are close. So let's do one more here, one more example. This HClO4. This is a neutralization reaction. Okay, the acid and base. So perchloric acid plus sodium hydroxide goes to water, which is our neutralization, plus sodium chlorate, ClO4. Okay. Is that balanced? It's balanced to me. So there's your molecular equation. This is a liquid, so this does not break apart. This is aqueous, and this is aqueous. So all those break apart. You want to write your net ionic equation. So you have H plus, it's an acid, plus ClO4 minus, plus Na plus OH minus. OH minus goes to H2O plus Na plus ClO4 minus. Okay, spectator ions.
Na plus.
Na plus
Chloride.
and chloride.
Yeah.
ClO4 minus.
ClO4.
You got it. So your balanced ion net ionic equation is H plus OH goes to water. And the last part of the question says, which are considered spectator ions? You would circle Na plus and ClO4 minus. All right. We got a couple more questions from another person here. They sent these in. And these look like ones from, trying to pick these up here. Okay, name the compounds. Okay, this is good. This is a good review for everybody. Any questions on the neutralization or the ionic equations? I guarantee you'll see that on the final. Just got done putting those in. Okay, let's go back and name some things. It said name CrBr3. Pull up your periodic tables. So what's Cr? Cr is right here, right? Cr is chromium. Okay, so you put chromium. And what's bromine? What's Br? Bromide. Is it bromine when it's in the end of a combination? Change it to IDE. Remember the metal keeps its original name from the periodic table. Okay, the non-metal you change the ending to IDE. So chromium bromide, but we're missing something. What are we missing?
Roman numerals.
Roman numerals. Perfect. How do you know you're missing Roman numerals? Because it's a,
Transitional.
metal.
you got it. It's a transitional. How do we know what Roman numeral to put in there?
Crisscross, so it's 3.
You got it. Perfect. Okay. Bromine has a -1 charge, there's 3 of them. So it's chromium 3 bromide. That's your answer. NO is nitrogen, right? You just give the first one its name. This is a this is 2 nonmetals, so it's a covalent compound. So this one you have to name the subscripts. We never name the subscript 1 if it's on the first one. We name it on the second one though. Remember, like carbon monoxide. You don't say monocarbon monoxide, it's carbon monoxide. So this is nitrogen monoxide. First one gets the original name. Second one is an IDE ending. And we name the subscripts if it is a covalent compound. We never name if it's a ionic compound. This is ionic, so we didn't name the subscripts. We just told you the charge. We didn't say chromium tribromide. Okay? So if we had N2O3, what would that be? Remember, name the subscripts. If it's because they're 2 nonmetals, they're both to the right of that line in the periodic table. So this would be
Sodium
dinitrogen. You got to name these subscripts. Trioxide. Dinitrogen trioxide. I think we had some more here too. Got that one, that one. Okay. Another one that was in the text question was this one here. And it was a Lewis structure. So it's oxygen. We double bond to arsenic. Double bond to oxygen. This is a funky Lewis structure. I wouldn't expect you to be able to draw this one. And it's just his name that compound. So what we have is arsenic twice O5. Okay. Again, covalent compound. Okay. There's no plus or minus charges here. See, it's all bonded. So it's di arsenic. And what's 5? 5 is penta, like a pentagon. Pentaoxide. So diarsenic pentaoxide. Is that making sense?
Yeah.
Here. And now it says write the formula for each compound. Aluminum phosphate. That looks funny. Okay, I think the person that sent it, because those are right, like aluminum phosphate. Again, ATE and you know it's a polyatomic ion. So you know you have aluminum and you have phosphate. Aluminum is +3. Phosphates minus 3. So it just combines Al, PO4, 1-to-1 ratio. So be careful with the crisscross. It's not 3 and 3, it's 1-to-1. That's the part you gotta be careful when you do the crisscross one, because just gotta make it balance. Now, on your answer, it looks like you gotta be very careful you don't put a capital I instead of an L. That's what it looks like, or a capital L. It's not a capital L, it's a small L. Okay, and the computer get it wrong. Be careful with your L's and your O's. Don't put an O for a 0 or a 0 for an O, because the computer will mark it wrong, because it doesn't know the difference. I can see what they did there. It's just, you got it right. It was just, there's a couple more here, I think.
I'm sorry, was it an L?
It looks like AIPO4 for the answer that they put on there. It's ALPO4. It's either an I or capital L.
Okay.
It's not a lowercase L. That's just a simple mistake on the keyboard. Does that
Okay.
make sense?
Yeah.
Okay. No problem. And then there's another one here. Like I said, the big thing is I's and L's and O's and zeros. Those get mixed up all the time by students. And there's another one, nitrogen trichloride, and then P4O6. It says name that. Who wants to name that? Is it ionic or covalent, first of all? Is it 2 nonmetals or a metal and nonmetal?
2 nonmetals.
2 nonmetals, perfect. It's covalent. Covalent compounds, you have to name the subscripts. So what's 4? 4 is tetra.
Tetraphosphate.
Not phosphate. Phosphate's a proton ion. Phosphorus. Phosphorus. Remember, the first one gets the name that's on the periodic table. The name on the periodic table is phosphorus. So it's tetraphosphorus. And then 6 is hexa
Oxide.
oxide. That's it. Tetraphosphorus hexaoxide. That's P4O6. Which one configuration? P3, okay, this was one of the 1s2, 2s2s also. So let's do P3 minus. Let's do the electron configuration for that. Now look at the periodic table. And we're going to go across to phosphorus right here, right? So it's 1s2 going across, 2s2, 2p6, 3s2, 3p3. But it says 3 minus, right? So 3 negative means 3 extra electrons. Electron configuration is your name of the electron. So there's 3 more electrons on it. So if you look at that, where am I at? P3 minus. So it's 1s2, 2s2, 2p6, 3s2, 3p, and it would be 3 for phosphorus. But this 3 minus means there's 3 extra electrons. So we're going to add 3 extra electrons to this. So it's now going to become 3p6. Okay. So that's the electron configuration for P3 minus. Now it also says what the atomic symbol for the noble gas that has the same electron configuration. So again, look at your periodic table. Look at phosphorus. So the noble gas that has the same configuration is what? Is argon. Okay, so it would be AR for your atomic symbol. Okay, remember, these are very stable. All the noble gases, everything wants to be like it, so it's very stable. Okay, and an isoelectronic series means something has the same number of electrons. Okay, like P3 minus would have the same as S2 minus, which is the same as Cl minus, which is the same as AR, which is the same as K plus, which is the same as Ca2 plus. all those, that's electronic series. Every one of those is going to have 18 electrons. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6. And you count them, it's 18. So every one of these is going to have the same electron configuration, the same configuration as argon, which makes it stable. It is not argon. They're different elements, but they have the same electron configuration because that's how they stabilize themselves. Those are the charges that we associate with it. And this was called, and you need to know this for your midterm, isoelectronic series. Okay? Same number of electrons. Remember, if you have a negative charge, that means you're adding electrons because electrons are negative. If you have a positive charge, you're losing electrons because now you got more positive charges in the nucleus. You've lost an electron. You've lost a negative charge. Now you become more positive. Okay, that makes sense? Remember electrons in each energy shell.
Do you have a study guide for the midterm?
What's that?
Do you have a study guide for the midterm? Or can we have like a day where we can meet with you and you can kind of tell us what? Or
Yeah, I'll make sure to make some time available for questions and stuff for midterm. But I don't have a study guide per se. But we can go over all the stuff from the chapters. That's no problem.
is it going to be from chapter 1 to like right before the midterm? I don't know what chapter.
It says, I think it's 1 through 9, right? I think it says it right on the syllabus.
So it's going to be, that's going to
I
be.
think it's
on
1
the
through
midterm.
9. Yeah, number 9 will be on the midterm. I think it's, I can put my syllabus right here. Chemistry documents. Syllabus. Where'd it go? Oh, there it is. Yeah, July 9th, chapters 1 through 9.
And it's going to be from there's going to be questions from every chapter.
Right, from chapters 1 through chapter 9.
How many questions total?
It's 150 points. I think it's 73
Oh, okay.
questions total. There's true, false. Multiple choice, matching, things like that.
Is it gonna be on sapling as well or somewhere else?
Maybe on sapling as well.
Like for the
No,
example, how
no.
the home,
This will be on your Canvas. Just click on it, go right to the midterm.
okay.
Yeah, this will be on Canvas. Okay. And I think someone had one more question on, it says, enter the number of electrons in each energy shell for each of the elements. So it says hydrogen. I'm not able to move down the rest of it. But for hydrogen, it says N equals 1, N equals 2, N equals 3. So those are just these numbers right here. So in this energy level, hydrogen has 1 electron. In this energy level, it has 0 electrons. And this one has 0 electrons. This all comes up on my screen, but I'm sure there's other elements. But just look at the elements, you can see how many electrons go across there. So hydrogen has 1 element in the N equals 1 electron, and has no electrons in N equal 2 or N equals 3 levels. Okay, I think that was all the questions I've got on my emails. I think I got.
I actually sent you a bunch, but for some reason it wouldn't allow me to send. So I guess it didn't go through in the emails.
I got the 2 from you.
Oh, is it from chapter 4?
It was the one that I did at the beginning of the energy of the blue light.
Yeah, I remember that one.
Okay, you got that one now?
Yeah, I got that one down.
Okay, and the other, okay. Yeah, those are the two I got. I didn't get anything else from you, just those two. I got some from chapter 6 and some from this last chapter 4. Okay, so I guess we covered that. Any other questions that we got? I know it's a lot of material, a lot of stuff.
I do.
Sure, go for it.
So it's on chapter 4 homework, and it's question 18 of 30, and it says, enter the number of electrons in each energy level shell for each of the elements. And so it says H, so hydrogen, N equals 1, and then it's
Right.
blank. And N equals 2, and it's blank.
Right. That's what that's this question right here. For N equals 1, 2, and 3, these are these numbers right here. That's what those are referred to, energy shells. So hydrogen has 1 electron, and it's in this first energy level. Okay. Has no, because hydrogen only has 1 electron. So it has 0 in the N equals 2 and 0 in the N equals 3. The only place hydrogen has an electron is in N equals 1. And if you had helium, helium would have 2 electrons, and they'd both be in the N equals 1.
What about for N equals 4
If
for
you look at
hydrogen?
It's still 0. Hydrogen only has
Oh.
1 electron. It's only in the N equals 1 level. Anything after that, it has no electrons in. But now, if you like lithium, lithium has 2 electrons in the N equals 1, 1 here and 1 here, and 1 electron on the N equals 2, and 0 electrons in the N equals 3, because it has 3 electrons. That's how it fills its shells. So for N equals 1, N equals 2, N equals 3, if we did lithium, it would have 2 electrons in N equals 1. Okay, that should where hydrogen and helium are. You had 1 electron in the N equals 2, that's this level right here. And then N equals 3 would have 0, because there's nothing past that. Is that making sense? It's just telling you where the electrons, it's actually where the electrons are, what energy level. And you just look at the periodic table and see where it's located. Does that make sense, Cassandra?
Sort of.
Well, here, look at carbon right here, okay? How many electrons does carbon have in the N equals 1 level? Remember, N equals 1 is only this right here. So how many electrons are in there?
1.
No, there's 2 elements. There's 2 elements, right? Hydrogen and helium. So it would have 2 electrons in N equals 1. How about the N equals 2 level? It would have 2 electrons from here and 2 electrons from here, 2 in the S and 2 in the P's. So it would have 4 electrons. And the N equals 3, it would have 0, because it doesn't go that far. Those just start with sodium. So it's just counting your electrons according to these numbers right here. So this row is N equals 1. This row is N equals 2. This row is N equals 3. And the electrons are just where it's located in the periodic table. So in N equals 1, you have 2 electrons, which is your 1s1, 1s2. In N equals 2, you have your 2s2, 2p6. You have 8 electrons total for like I went away to neon. But if you had carbon, there's 6 protons, there's 6 electrons. Does that sort of make sense?
Yeah.
Okay. Gonna mess my periodic table. Other questions?
Yeah, I had one. If nobody else has one right now.
Sure, no problem.
Okay, so
What you
this
got?
one is still on chapter 4, and it's question 26. And it says, write the full ground state electron configuration of O2 positive.
Okay. Again, let's go back to our periodic table. Okay. And here's oxygen, right? How many electrons does oxygen have?
8.
Right, perfect. So you go back, you have 1s2, 2s2, 2p, you go to oxygen, 1, 2, 3, 4. Now, it says O2 positive, right? So you're missing 2 electrons. So instead of having 4, you're only going to have 2. So that's the ground state, 1s2, 2s2, 2p6, because you only got 6 electrons, because O2 positive means you've lost 2 electrons. Make sense?
Okay, so it's 1s2, 2s2, 2p2.
2p2, because you've lost 2 electrons. You're isoelectron now with carbon.
Oh, okay.
It's not carbon,
And-
but it's just same electron configuration as carbon. Does that make sense?
Yeah, and then there's an additional question after that one, and
Okay.
it says, which neutral atom is isoelectronic with O2 plus?
Okay. So O2 plus has, you said 6 electrons, right? So what neutral? Well, oxygen has 8, but
Yeah.
O2 plus has 6, right? Because you've lost 2 electrons. That's why you have a positive charge. So it's isoelectronic, same electrons as carbon, as neutral carbon. Because carbon has 6 electrons, and O2 plus has 6 electrons. Just like F3 plus. I can't draw an F. F3 plus would have 6 electrons. Nitrogen plus 1 would have 6 electrons. Those are all isoelectronic with carbon. Every one of those has 6 electrons. Carbon, N plus, O2 plus, F3 plus, all have 6 electrons. Because for every positive charge, you've lost 1 electron. For every negative charge, you've gained 1 electron. Does that make sense?
Yeah.
Okay. Perfect. Keep that one clean so I can write on it. All right, other questions? No more questions? Or is everybody all questioned out for one night?
I have more questions, but I was just waiting to give other people a chance.
Okay. What other questions you got? I think anybody else is just waiting for yours, I guess. What questions you
I
got?
think we're all too embarrassed. I am.
Oh, no, don't be embarrassed. There's nothing to be embarrassed about asking questions. That's why I'm here. I love questions, so not a problem. Never be embarrassed with questions. What else you got? Is there more, Cassandra?
Yeah, since nobody else seems to be asking.
I'm sure they all have the same, so everybody has the same questions you do. They're all learning from it, so no problem. So ask what you got.
Okay, I'm gonna go to chapter 5 homework. For some reason, it didn't send when I tried to send it on email. I don't know why.
Okay.
Okay, so number 16. Says, write the chemical formula for the compound formed by each pair of positive and negative ions. So
Okay,
it says Ba2 plus and NO3 negative.
okay. So what would you write? This is what we've been
Was the
doing, right?
first one,
Pause is always first. Then you make them balance. BaNO3 twice. They said the crisscross, 2 goes here, 1 goes there. Because everything has to be neutral. Barium's positive 2, nitrogen's negative 1, so there's 2 of them. So +2 and -2. You gotta make sure every compound is neutral.
okay. I get that one now.
Good. More bottles.
Okay, I have a question that I'll finish my lab too if I just answer this question. I can't seem to get it. It says, the simulation allows you to measure the masses and volumes of various solids. Arrange the solids from highest density to lowest, and I did. It's gold, lead, and iron. And then the second part of the question asks, what is the density of the solid with the highest density of the 3 given solids, which is 386.2 grams per milliliter is the density of gold.
Okay.
So I don't know, I don't know what to put in there or what it's asking me really.
It said arrange them in order of the highest density.
Yeah, so I did that part. I got that part right. Gold being the most dense, then lead, then
Right.
iron. And then the second part of the question says, what is the density of the solid with the highest density of the 3 given solids? And I put in what it weighs at, which is 386.2, but I think it's wanting me to convert if I'm not mistaken.
I'm having a hard time hearing that. It's asking for the density of the actual density of the greatest, the solid that has
Yes.
the largest density.
Yes.
It would be just the density of gold then, yeah.
Yeah, and no, but the second part of the question is telling me it's wrong.
Tell
What
you
is
it's wrong.
Yeah, because I put what, so it says, what is the density of the solid with the highest density? And I'll tell you what the feedback, oh, the feedback's wrong. Yeah, so I arranged it in the correct order, which is gold, lead, and iron. And then there's a second part. It says, what is the density of the solid with the highest density of the 3 solids? And I
Would be
weighed
the
the
density of
gold.
gold. That's what it's saying.
Yeah. And I weigh the gold and I put in what it tells me and it says no.
What are you putting for an answer?
386.2 grams.
No, that's a mass.
No.
That's not a density.
Okay. So I have to convert that.
It has to be it has to be in density, grams per milliliter. It has to be grams per milliliter. That's density, mass over volume. That's what's giving you some trouble.
386.2 times 1 over.
Yeah, it has to be used of grams per milliliter. Maybe just putting the wrong units on it with some. Okay. Does that make sense though?
Kind of, how many?
It has to be in density. It's asking for density, not mass.
So I have to do that. I have to convert the grams to grams per milliliter, right?
What's the density of gold? Didn't you already do that?
I just weighed it at 386. And oh, when I put it in the cylinder, it's
That's mass.
120 milliliters when I put it in the cylinder.
What did the cylinder start at?
100.
Okay, so the gold weighs 386.2 grams, right?
Yes,
And it went from 100 to 120 when you put it in the cylinder.
yes.
So density is mass, which is 386.2 grams, divided by your volume. Your volume increase was 20 milliliters.
I was dividing 120.
So 386.2 divided by 20 should give you your density.
19.31. Yep, it's correct. Thank you. Sorry. It's because I was
Got it.
dividing it into 120 milliliters.
No.
But
It's
it's
how much
the
of-
displacement. Yes.
Right, how much of an increase? Perfect. You got it. Good.